Yeah, thanks for the nice introduction and such a lovely program. I'm Anthony. I'm funded by the Simons Institute and the Challenge Institute for Quantum Computation. I'm also grateful for the PIs at Berkeley and MIT for allowing me to be at both the places. This is work with my student Thiago, who will also be here, I guess, in a week. And I guess I'm also grateful for the organizer and Ewan for some last-minute scheduling changes. So that was also very helpful. And then I guess when did I actually think about how did I come to this problem? I think it's because about 1.5 years ago I was visiting Ken B's and we discussed some problem, and this was one of what triggered me into thinking about this problem. So that was a thank for him. Let's get started. Okay, so it turns out, this problem can be stated in one slide, so I'll just let you know what the result is. So if you consider a 1D quantum system, so literally this means a bunch of qubits interacting on a line, and then you now say, okay, I'm going to put this quantum system in some bath, and then it claims that this process always quickly equilibrates. So there's some fairly generic kind of setup where this always happens. And then you can sort of state it more precisely once you pick like a specific kind of Markovian model of this dynamics. So this already be featured a lot in this conference. And the claim is that if you choose this dynamics and has d-Hall balance, then this would have a system size independent spectral gap. Okay, so that would mean that this process converges quickly. And then so I'll be more, I will quickly set up how to define all the specific parameters in choosing these lim-Nodians and then the formal result. And then it turns out that now when you have a gap, you actually also get a lot of other things for free. So that's also like a hidden bonus here. And then I'll tell you how this proof goes. And there's actually some new thing we learn, not just this result, there are actually some techniques we learn. And then in the end, because I know the experts are interesting to go beyond this result, so I will give a hint on that as well. Okay. Any questions so far? No questions? Maybe? Okay. So let me just start. Okay. So I guess one slide of a very, very quick motivation. This have already show up in the morning, but just to be self-contained, part of the reason, the hidden, long-term motivation for why we're studying all these quantum Markov chains in Vadian. At least one of the reasons is that we would like to simulate these interesting quantum systems, and whether you're interested in chemistry or material science or physics, we hope that this Markov chains, this quantum version of the Markov chain would be a principled algorithmic framework to sample from the quantum Gibbs states. And today I'll be really doing just Gibbs states, but the ground state is its own big field already. But today we'll do Gibbs states. And then we still hope that this algorithm would tell me a lot about the features of these models, right? Energy, phase diagram, etc. Okay. And then sort of under this big motivation, the way to view our today's results is, is like this, right? So 1D, these systems, all these interesting systems are not really going to be 1D, but hopefully, this 1D result give you a concrete, at least example that telling you that these Markov chains could be a very principled and improvable framework to study these algorithms, and also sometimes it could be optimal. Right? So at least it's a very concrete instance that you can really know what's going on, and hopefully this gives you more motivation to keep going on exploring this direction in more concrete and more complex 2D, 3D settings. Okay. And then again, just to make our talk fully self-contained. This will be the type of object, the mathematical object we're interested in. The state space are going to be this quantum state, PSD, normalized matrices. And then our evolution are going to be this continuous time lim-Nodians. Okay, so whether they call lim-Nodian or master equation, to me, right now, for today, it is all the same. And then in particular, there are some mathematical structures for, structure theorem of what they should look like, and there is some canonical form. It doesn't really matter so much what these exactly are, but I'm just saying that there is a canonical form, and then sort of the interesting point is to choose the specific one that has other structure. So right now this is entirely abstract, but then there will be specific choices, such as the one that was mentioned in the morning, and the one I guess I put on the board. Okay, so there's a specific instance. Okay, So for today, the state that we care about is 1D system. So what does that mean? It means that the Hamiltonian we're interested in is really a line, kind of really put it on the line, and let's say there's n qubit. You can count it 1 to n, and each of the local dimension is 2, just for simplicity. And then the Hamiltonian is really just going to be the simplest possible, which is nearest neighbor, right? You can write down h1, 2, h2, 3, and then you just add them up. Okay. And then to normalize it, we're just going to choose each term to be a norm 1, but this is really just a convenient convention. And in particular, what's interesting here is that this is non-commuting. Okay, so if it's a classical Hamiltonian, they would be commuting, right? So when they touch on the second qubit, classically they would still be commuting, but in this quantum case, they would not be. Okay, and this is the source of difficulty and why this problem is non-trivial. Okay. And then if this is a Hamiltonian, you can define a Gibbs state. This already shows up a lot of time, but just to write it down, it's the exponential function of the Hamiltonian. Okay, and then there's this beta you can tune. Okay, so 1D Hamiltonian probably shouldn't surprise anyone. Okay, and then sort of the way we set up this problem, I think already hinted in the morning, is to consider a Lambdatian, right? And then and this is sort of like a generic statement, right? So recently there's been this construction that if you choose a Hamiltonian set of jumps and inverse temperature beta, then you can turn this into a KMS detailed balance quasi-local Lambdatian. Okay. And then there's a fairly general and fairly explicit constructions. Now there's a big list of them, and then some of them are not there are some of them that are KMS quasi-local, some of them they're not. But these are all kind of families of Gibbs samplers you can choose. And for today, we'll be sticking to the CKG version because somehow analytically it's a little cleaner to, well, I don't know if cleaner, but like at least it's possible to do some of these calculations. But I believe that this could be extended to other ones, but I haven't fully checked. And then for today, we're going to instantiate this sampler in 1D, right? So again, this is a figure I showed you. You're really just considering you're putting your quantum system in a bath, right? And then each of them is now being kind of thermalizing with some bath, and happens kind of in parallel. And now, in order to capture this physical kind of model in mind, we're going to pick all these kind of this jump that as our input of the algorithm as all the possible single polys, right? So there are 3n of them. Okay. And that would sort of means that you have some kind of extensive Lambdatian that acts everywhere at the same time in parallel. And then if you count like a norm, this is going to scale with the system. Okay, so this is really a physical kind of everything act at the same time.
Your spin chain model, is it like a chain of spins that are just connected to nearest neighbor, or do you allow for next nearest neighbor coupling?
So in our paper, we actually handles all the other cases, but today I just think qubit nearest neighbor. I think that captures essentially all of morally everything. Yeah, but you can change this a little bit. Yeah.
Just related to that, so I guess this result would work as long as the support of the interactions is non-extensive in system size or something.
Yeah, I mean, you can coarse grain it, and then as long as it's effectively as long as it effectively can fit into this model, and then by blowing up the local dimension. Yeah. Yeah. But then things would start getting worse when you do that. Yeah. But here really the point is that you kind of want like asymptotically like a 1D system. And n is the parameter that you make bigger. You fix everything else. Yeah. Any other questions? Yeah, because this is the model, so it should be very clear what this is mathematically what it's supposed to do. Okay.
So the norm there, you have this diamond norm. Why are you using?
Oh, I guess I just want to say this it is extensive, so I guess you can use one norm, but diamond norm is slightly stronger. But yeah, so you can just think of it as one norm in trace distance.
So there is a technical thing called the diamond norm, but you're not using that.
It doesn't really matter, but yeah, you can just think of it as one norm here. Yeah, it really just means a trace distance. Yeah. Any more questions? Okay, so this is what we call like a 1D Gibbs sampler. Right? So that should be clear. And then the main question is, what is the spectral gap of this process? Right? There's a Markov chain. There's like a detailed balance. Then you can ask, what's the gap? And if you have gap, you get lots of things. One of them is mixing times. That's one of the things we can get. But also actually also give you other things. Okay, these I will actually go through these other consequences, which actually turns out to be also quite interesting. Okay. So here's the main result. Just to write in text. So for any 1D quantum system at any fixed temperature, the quantum Gibbs sampler, especially the CKG family, has a system size independent spectral gap. Okay. So it turns out this is like the right scaling, it's optimal scaling, and then you can like chase the classical result, and this is the one I found. Was proven like I guess 30, 40 years ago. Yeah, so this is like a very classic type of result and one we expect and it should be true. And we proved that this is true. I guess I made a table here that probably would miss some of the results. But so just to give a context of what people have been doing in this kind of mixing spectral gap kind of question, this domain, there has been like a pretty long line of work in commuting case, date back to I guess 14, and I think there's even older results that I'm missing here. But people have been studying commuting Hamiltonian where you can do Davies generated, okay, and then you can already start proving mixing time. And 1D was basically fully understood. It has spectral gap and I think even entropy decay.
Sorry, the commuting H is commuting with what?
Oh, I guess the neighboring, each term commute with each other. Yeah. So in our case, it's like, if they overlap, they don't commute. That's our, yeah. But in this case, everything commutes. So the light cone is like finite. Yeah. So that's yeah. And then in higher dimensions, because there could be phase transition, and one has to put assumptions in order to prove like this mixing, and then. Now I think it's still an ongoing industry. I think the expert could help me. That it's still ongoing industry to really pin down what's the right clustering assumption, and that would lead to fast mixing. Okay. But in the non-commuting world, this is a lot more recent, and we actually see a lot of these in this week. So I will not really say too much. But so today this is kind of where our result fits. We kind of try to handle this 1D. Specifically for KMS detailed bands, quasi-local. Okay. And then somehow the techniques seems quite different from any regimes of these other kind of high dimension kind of more perturbed results. So it looks like there could be a nice synergy here. So they're not really directly related. Okay. Any questions?
What do you mean by perturbative?
Yeah, I think they'll tell you. I mean, this code means that there's like a simpler Hamiltonian. You add epsilon v. Yeah. So you should watch. You should look at their talks. Yeah. Any more questions? Okay. So. So it turns out, to fully explore the power of a spectral gap, it turns out one have to look into this parent Hamiltonians, which is something that it actually came out already, 2 years ago or even earlier in the literature. That there's like a general idea that whenever you have a detailed bands Lambadian, you can try to think about sort of the purification. And classic, this type of idea is already kind of present in the secretive walk construction. So this is not entirely new, conceptually not like fully new. But then in this specific case of Lambadian and so apparent Hamiltonian, turns out this could buy you more, and also turns out mathematically very natural. Okay, so let me still kind of go through them, right? So you have this Gibbs state, which is a mixed state, and then you can kind of map it to like a pure state. Now, once you kind of purify the other kind of, it turns brought to ket to brought, like you kind of have another system and you purify this. And then there's like a very kind of very natural mapping, right? Lambadian maps to a parent Hamiltonian X on this system. And this parent Hamiltonian is self-adjoint, which is the same as saying the Lambdatian is detailed balance. And fixed point become like a zero eigenstate condition. However, what's interesting here is that here you have a Markov chain, but then in this purified world, it's not really like a Markov chain. Then you have to run something else, which is like some adiabatic process. Okay. But here, really, the catch is that people have been doing a lot of work in understanding gap ground states, and a lot of them is by Hastings. And this one, for example, if you have a gap ground state, it's known that it always satisfies some exponential decay of correlation. Right? This is a very classic result. And then if you have a gap adiabatic path, it's also known that it will give you a polylogarithmic depth ground state preparation. Okay. This is, I guess, is under the name of quasi-adiabatic continuation or something like that. So a lot of this is like known in the ground state world, but now because of detailed balance, I can just kind of lift all of them in the Gibbs state case. Okay. Any questions? Okay, so let me just show you some of the nice consequences. So since we have a gap, and if I just use Hastings-Comas correlation decay, you directly get that any 1D Hamiltonian at any fixed temperature has exponential decay of correlation. Okay. And because it's 1D, there's really not many different geometries you can choose, just kind of ABC, right? And these are all intervals. And then here, correlation sort of, this bracket just means kind of trace. You take trace against your state. So this is really like one of the most natural notion of correlation, xy minus x times y, right? And then this we can prove that this always decays exponentially. How interesting is this? Well, exponential is the optimal rate, right? You can look at some classical example, and this kind of matches this. This is exponential, so it's hard to get much better in general. And then I guess to those of you who might come from more like mathematical physics or statistical physics background, this is like a very, very classic result by Iraqi, who proved like a 1D translation invariant case in, I guess, 70 years ago. So 50 years ago. And then we finally kind of generalized this entirely to a non-translation invariant case. And here, like the technique really used like the fact that it's like translation invariant and it's infinite. But here, we have to go like a long way to prove the spectral gap of the mixing process and then come back to prove that the static kind of the Gibbs set has a correlation decay. Yeah. So, and then what's kind of nice is that this decay of correlation really kind of is an important idea. And then in our proven spectral gap, we actually use this very recently proven sub-exponential decay as an input in order to fit into the spectral gap, and then it comes back and gives you exponential decay. So there's like a very tight kind of how these things kind of fit together to give you like this exponential decay.
Yeah, so in this result, does the constant mu and alpha depend on the size of A and C?
No.
No. So they are uniformly.
It only depends on the temperature. So A and C could be the rest infinite. Yeah, it could extend to the infinity. Yeah. Yeah. So it's actually like very delicate once you want to take care of all possible kind of correlation decay, and then there's like a gazillion of other things you can try to write down. Yeah. But it turns out in 1D things are kind of nice, so yeah, they're not too different. Any other questions?
So when you say spectral gap implies exponential decay of correlation, like it's not. So here it's not a direct consequence of spectral gap.
It is.
So, but it's especially in 1D. Because I think in a general case, in high dimension, you need to restrict the size of A and C.
Okay. Yeah. In that. Yeah. That's true.
You can do something stronger.
Right. In higher dimension, then you have to choose a geometry, right? I haven't told you how to choose, but I'm just saying that. So this proof is really just import correlation. Just import Hastings-Comas. Yeah, this proof really just come from that.
You said that you use an a priori sub-exponential decay to prove the spectral gap, which then implies the exponential decay. Can you then like bootstrap this method and like get a better estimate for the constant?
Somehow
now using
exponential is the right fixed point. Yeah, I guess.
Like, I mean, I don't mean to improve exponential decay, but maybe you could improve the constant by now using that you have exponential decay or something like that.
You can probably improve it somewhat, but I don't think you'll get a tight.
No.
I think it's pretty hard to get a tight count. At least I don't know how to like obviously do that. You probably have to do some very specific calculation. Yeah.
Is exponential decay optimal, or could it be super exponential?
I guess it's optimal in general.
So is there a matching law of
I guess like if you take like Ising model, it seems Because Ising model you can write down like some transfer matrix and that would just be exponential. So.
What is the sub-exponential decay? Like, what can it be, the sub-exponential decay? You know beforehand that there's some...
I think they prove like... They actually have lots of results. So you have 1D long range, 1D short range, etc. And then I think the one we actually don't need... We just need any kind of decay that's faster than R squared or something. But they have some I think e to a root r or something, and we just directly use that. But it's somewhat flexible. Yeah. Okay, any more questions? Okay, so that's correlation decay, and the other thing is maybe it's slightly more to the heart of this audience is that once you have a spectral gap across a range of temperature. Then also give you like a very local looking kind of almost optimal quantum algorithm. Okay. So the claim is that you can prepare this purified Gibbs state in a polylogarithmic depth. And here I guess there's also an Celia that was not drawn, but but roughly the picture looks like you have these two copies of your state, and you have this block of polylogarithmic blocks of quantum gates, and then the state kind of can be formed in this way. Okay. And then I guess previously, people have done a lot of 1D work, so we're not trying to beat them, so much. But then at least in terms of the depth, right? Previously, if you're going to go through an MPO and then turn it into a quantum circuit, there's like, it somehow has to be like a deep circuit. Okay? So at least we can improve the depth. But in 1D, it's a little hard to beat classical algorithm kind of in too many directions. Okay? But anyway, it looks like this is fairly optimal and somehow give like a very intuitive picture. And then there's like a funny thing, which is we have to go through this adiabatic this purification picture to get like polylog depth algorithm. And then if you literally run the Lindbladian, right now, if you put together all the existing bounds, it actually requires poly n depth. So this is kind of I highly doubt this is optimal. The actual performance, but there's some loose ends in actually getting the right kind of bounds in the Lindbladian case.
So this polylog thing is from the spectral flow, right?
Yeah.
So there's like one small. I'm sure this is. You're starting from the zero Hamiltonian, right?
Yeah.
Which is not gapped. So how do you get around that?
Oh, so the Hamiltonian, sorry, yeah. So the parent Hamiltonian is not a zero Hamiltonian. The parent Hamiltonian
temperature is not zero.
When you have zero temperature, sorry, you have when beta is 0, the parent Hamiltonian is like I guess the Lindbladian is a depolarizing channel. Yeah. So it has a constant gap. Any more questions?
So whenever you say gap, you mean the parent Hamiltonian gap?
Yes. Yeah, because we're thinking about Gibbs states, where the ground state gap somehow doesn't really play a role.
Do you really mean poly n depth, not poly n gate count?
Yeah, I mean, the gate count will be n times, it will be n.
Also poly n depth.
Yeah, this I mean depth. The gate you have to multiply by n.
Yeah, Ronnie, the remark.
Yeah. Oh, yeah. The best previous requires.
That's last word.
Yeah. So the classical algorithm is actually efficient. Is n to the 1 plus epsilon. Yeah. But I guess the difference is that they have to first go through an MPO and then embed it into a quantum, and then embed it to a quantum circuit.
I believe the classical algorithm can be parallelized, so it can be more cost-effective.
Maybe it could, but I asked some of the authors, and yeah. Again, it's in the spirit, the sentiment, I'm not trying to say there's a big quantum advantage in this 1D system, right? That would be kind of too wild to claim, but there are some differences in these approaches. So really, again, like as I already said in the beginning, how to view this 1D result, right? Is to say that, there are cases where this Gibbs sampler could be fully, at least somewhat fully understood, and then it would sort of give you a hint that maybe it's also worked well in other cases. But yeah, so but this really should be like a benchmark that at least it's optimal in this 1D case. Otherwise, it will be pretty sad. Okay, any more questions? Okay, so let me tell you some proof ideas which I think could be, could inspire other work. So, it turns out we'll have to look back into what classical people do to do mixing time. I'm not really an expert there, but I'm very grateful to learn a lot from my CS colleagues. So apparently, in order to prove classical mixing, quite often you have to work very carefully with the Gibbs measure, and then you have to cook up some definition of correlation decay, and that could mean lots of different things. And then you have to work very hard to get the right version, and then that somehow allows you to do some recursion to get spectral gap or even something stronger. Okay. And without really going into all these details, I'm sure you can find very kind of good surveys on how these things are done. But really for the quantum case, the question is like, okay, how do you actually go about this in a quantum system? Right? How do you actually define this thing? And there's like a type, kind of just even write down the right type of things is not so obvious. Okay. And then they somehow give rise to fairly annoying obstacles, which is we know that quantum systems don't like to be measured. Right? And then quite often if you measure anything, it gives you this disturbance, and often it can also lead to non-locality. And then there's kind of two things that the classical people really like to do when they think about mixing times. The first is that whenever I'm giving a bunch of spins, I would like to condition on boundary. This is almost in a lot of the mixing time paper, this is one of the things that I do every time. And the other is that the Markov chain itself is local. And these two are both kind of very useful, and now I'm writing it down painfully explicitly. Okay? And then even in the commuting case, you preserve, I guess, the locality, because Davies is local in the commuting case. But you already have to give up a little bit on how to think about conditioning. Right? And then this work by Castellano and Brandao, they have give you some recipe of how to do this in the right mathematical language. So I put a exclamation mark so that this requires some change of thoughts. But then what about non-commuting case, right? So it turns out even to even have the right picture of what it means to be conditioned on a boundary is very, very subtle in non-commuting case. So there's another question mark here, which is already there are some ongoing progress in trying to understand this already. And this is already fairly recent. But even this part is not fully understood. And then there's like a kind of a even more serious problem, which is, as we've seen, quasi-local is somehow a salient feature of this Lindblad dynamics. Right? So this is just truly false. And this somehow brings along lots of problems. Okay.
You say truly false. Is it proven to be false, or it's just we believe strongly that it's false?
I believe strongly, and then I have some. I guess I can probably prove it's false under some conditions. But if you can somehow make this local, I think it will also have nice consequences. So yeah. But it looks like you have to remove. Okay. Yeah, let me say the strong belief now. So, but we can chat more. So this question actually came out during lunch. So, so okay. But at least so right now our world view is that this is false. Okay, so we just assume this is false. Okay, so how do we do it? So let's actually go through the strategy of Castellano and Brundle, which go understand this paper very, very well. Okay, so the first step is to define like a very nice object called conditional expectations. I guess, let me just say the specific type of conditional expectations. And physically, this really just means that I'm going to activate some of my term in the Lindbladian and then run it for a long time. Right? And because I only activate for like a subset of terms, it doesn't really touch anything else. Okay? And I'm going to denote this by EA if I have a set I want to kind of resample. And then you can write down a laundry list of nice properties. This all really makes sense, right? Detailed balance, it's trace preserving, projective, probably positive. There's like all the properties that really make a lot of sense. And then once you have these objects, it turns out like a very nice thing to think about is like a strong clustering condition. Okay. So somehow this captures the fact that this system is has decay of correlation, and this is like the specific one that I wrote down. It's still very mysterious to me how to really think about this, but mechanically it's quite simple, right? It's just to say, if I do this on AB and do it on BC, it's the same as doing it all on ABC altogether. So mechanically, it's not too hard to imagine that this could turn into a recursive proof of kind of gluing smaller to bigger kind of regions. Okay. Okay, so this is the recipe, and then once you define this, and if you're able to prove it, then this gives you a way to kind of recursively build up local gaps into bigger pieces and eventually get the global gap of the dynamics. Okay, so this is the strategy of Castellano and Brundle. Okay, so what's the issue here? So in our case, because we're dealing with non-convening Hamiltonians, the issue is that this tiny tail, even though people often kind of think that is essentially local, in this case, this tiny tail actually is a problem, right? Because if you take any of these and you have this tail supported everywhere and you run this for infinite time, there's like an order of limits happening here that even a tiny tail could eventually become very, very strong, can act very strongly on your system. Okay, and this somehow change the entire picture, right? Because if you just one step, even the first step of this recursion has just already turning globally, and then you can't really think about local gap because this local gap would be exponentially small in this case. They somehow just break the recursion. So it really changed the picture because of this quasi-locality. Yeah. So again, if you somehow have a way to make this truly local, then it would somehow changes the way to approach this problem. But right now, the quasi-locality is a problem. Okay, all makes sense. Okay, so then what do we do, right? So it turns out we might have to go kind of in a very wild way that almost like an out-of-body experience. So we have to introduce something that's non-physical. Okay, so this is really weird, and you should feel very uncomfortable. But it turns out what we found like a useful idea is a relaxation of conditional expectation. Okay, so we call it a spectral conditional expectation because for all the linear algebra properties, it does the same thing. However, I'm dropping complete positivity. Okay, that seems kind of weird. So this is a map that you cannot, at least I don't know how to implement physically. But this is still just some linear algebra object. Has all the nice property. And then it turns out once you relax this condition, it is possible to make this conditional expectation quasi-local. Okay, so if you just compare with the previous slide, so I claim that if you run this map for a very long time, it could kind of hit everything at the same time. However, in this case, there's like a well-defined quasi-locality for the conditional expectation.
I do have a quick question. So, why you want to run this map for a very long time? If we only care about the mixing in the A, there should be some missing time. So we only need to run until the
Yeah, so in fact, in the earliest, I guess some of the notes I trying to do it earlier, like you kind of can do without taking limit, and then introduce epsilons, and then I somehow wasn't really able to get a tight, yeah. But this somehow, yeah, just having like a limiting object makes things very clean and nice. And this, maybe there's a way around this, but at least in order to get like an actual constant gap, it looks like one really wants to have clean objects. And that's also how this KB paper done this. But maybe there's a way to take some clever choice of T and then choose it carefully. But yeah, that's a direction that to explore whether you can get like qualitatively different behavior there. But, yeah. Okay. Okay, so now now I introduce this kind of fictitious kind of a relaxation of conditional expectation, and kind of the way to get this is turns out to introduce also a non-physical generator that's not a Lindbladian. So it has everything else but not a Lindbladian. So it doesn't look like this KK dagger, doesn't have the Lindbladian form, but it has other linear algebra properties. Okay? But it turns out this guy is locally gapped, which we don't know how to prove for the original Lindbladian. But then what the picture is that if you run this for infinite time, it actually converges to this object. So this tail really stays there. Right? It's because these things converge very quickly, so it doesn't really have time to grow outside.
Is this new conditional expectation positive?
I don't know.
So you don't need any positivity.
Yeah, now we're just doing spectral gaps, right? We don't care about that. Yeah. But yeah, I think it'll be curious to really understand what this type of object are and whether they have any use anywhere else. This is just come out kind of construction for the proof, but I don't know if there's any other use of this.
I think since you require to be detail balanced, which means it's symmetric and also projective, then it is positive. It's not like it's self-adjoint, eigenvalues.
But that's in terms of the operator, not in terms of super operator. Like I think the linear algebra property, I think they're all the same. But then I thought positive sort of means that it maps positive to positive. So that's a super operator property. Yeah. So I don't know. So one should check, and maybe it is. But okay. So for the expert, let me just show you what this looks like. It looks kind of ugly. It's very explicit. At least that's good. I guess it turns out like the way to get this is actually to stare at the Dirichlet form. Okay, so here is how this was kind of discovered. So I dream about this Dirichlet form every day. This is like the Dirichlet form for the actual Lindbladian. And then you look at this, it looks kind of ugly. There are some integrals. And then kind of the annoying thing is that these a omega t's, whatever it is some kind of Heisenberg dynamic, some filtered operator. And then this thing is quasi-local. Right? It's very hard to get rid of this quasi-locality. Right? So then it turns out, if you try to remove all these things, you can try to propose this object. Right? And now this is just a commutator with a bare kind of jumps. Right? It turns out if you kind of open this up, you get this K. So it's kind of come from reverse engineering from this commutator. And then what's very nice about this once you have this very very explicit form, you realize that you actually know what the kernel is, right? This is just some kind of PSD kind of a square of something, right? So if if sum over k times x on x is 0, this 0 just means that each of them is 0, right? This is because it's sum of squares. And then I actually give you like a very explicit characterization of what are the kernels kind of, or the fixed points of this conditional expectation. And here, notice that this is strictly local. The kernel is really just everything has to be identity kind of on the system on the subsystem you care about. Okay, and this is really because of this explicit locality and explicit knowledge of this kernel that allows you to think about more local quantities. and then the recursion of KB. Okay. So here's like a proof outline that is really just to follow what KB has done. So let me just kind of show you what all the required steps are. We have to first prove this clustering condition, and then it turns out you just take all the paper you know that has written about 1D, and there are lots of them right now. So you stick all of them together, you can work very hard and then get this. And including imaginary time evolution, weak clustering, and so this exponential decay. You stack all of them together, and you can get strong clustering, and then that feeds into this recursion. Okay. But then there's one thing that's still missing, right? So if now I prove the spectral gap of this non-physical map, right? What does that really mean for the physical one? Right. So actually, there's like a missing step that we have to introduce, which is to kind of compare the gap to the physical map. So this is actually not trivial, and it is not, we don't actually know this is true until we actually write this down. But the claim is that the Dirichlet form, this quadratic kind of thing, actually has a very nice comparison between the physical one and the non-physical one. So really, linear algebraically, this non-physical map is actually very nice. And in particular, so this comparison is very lossless. It doesn't depend on the system size.
It's a Raki result. Is that the translation invariant?
Translation invariant 1D, yeah. But he also introduced kind of this, I guess, the way to bound imaginary time evolution, yeah, if I'm not mistaken. Okay. Yeah, I guess I still have a few minutes. Oh, 2 minutes, okay. Okay, so let me, I guess, quickly go through some discussions. So, yeah, so there are some nice points that, that we use in 1D that maybe would break in higher dimensions. So here's maybe some bridges to, hopefully the expert will find a way to go to higher dimensions. So one thing that we use a lot is imaginary time evolution, okay? And then in particular, we use the fact that in 1D, this specific object, this conjugating by this Gibbs state and you take norm, is actually constant, or like system size independent. So we use this a lot. It sort of means that there's some kind, if you write this operator in the energy basis, there's some kind of decay in the energy change that it could induce. And it decays really, really quickly, so that even if you conjugate with the Gibbs state, with the exponential, it doesn't, it's still kind of slower. So it's still, 6 minutes. Okay, great. Yeah, so, but it turns out, higher dimension, this imaginary time could be very crazy. So I think in the next few talks, I think this will show up again. So I think this is kind of interesting, which is that in higher dimension, this norm could just blow up. So a lot of things we do in the proof would just kind of not work. It would just give you e to the n. So that's kind of annoying. So I'm going to use this chance to advertise like somehow one of these tools that turns out kind of it could be useful, has been useful in some cases, which is how to regularize these kind of crazy looking like this conjugating by the Gibbs state, this type of object. This is and this is one of the constructions that came up in a lot of these Gibbs sampling instructions. And here, what really it is trying to do is that if you start with any kind of simple jump A, which have its own kind of matrix elements when, in terms of EI to EJ, once you introduce this operator for a transform, it kind of selects kind of a part of it. And then you can kind of select like a tiny part of it, and you would know roughly that energy is changed by roughly omega. And I can do this anywhere. And it turns out this is like a good way to understand this imaginary time conjugation, which is, if I start with any A, I could first do like a resolution of itself. I can write it in terms of different omegas. I just cut it into different parts. And then it turns out to be a useful thing to select like the low frequency part and the high frequency part. Okay. And this is a bad part that actually calls the divergence. and this is a good part. And then pictorially, once you do this conjugation, right, this thing actually could go very wildly. However, if you only look at this smaller part, it actually kind of are sharply confined, right? So this is like a trick to regularize these objects, and then it has been kind of useful in a lot of sort of other papers that appear around this year, regarding kind of learning in low temperature regimes or metastability. Okay, so this actually could be useful, and hopefully this would find its way to towards proving mixing time in higher dimensions. Okay. Another kind of theme is to go beyond spectral gaps. So I know there are many people here who love entropies more than spectral gaps. So I put this slide for you. So today we're really thinking about spectral gaps, right? And this, you can say this is some Poincare inequality. Really is in terms of linear algebra. Okay, but you can also ask, how do we think about entropy decay or this modified log-Sobolev inequality? I hope I didn't put any sign wrong here, but this type of decay of entropy. This is lots of people are interested in it. That myself hasn't really thought about this. But let me just comment that sort of one of the this non-physical map that we introduce is really for the linear algebra properties. And it itself doesn't seem that it preserves density operators, so that's kind of annoying. So that this part has to be overcome. And then in terms of approaching this entropy decay, just going to advertise that there's like an identity of what this d by dt relative entropy actually is. This appears in the metastability paper. Well, the claim is that there is an explicit expression of what this entropy decay looks like. It has some logs. It has some fractions of the state. It has some commutators, and you can kind of think of it as some kind of gradient squared, kind of. And maybe this would give you a way to, if you look at this and spend a long time, maybe this would open a way to study entropy decay. Okay? But right now, this is an open problem. Okay. So I will just stop here, and then thank you.